All right, today we're going to meet a monster. I'm talking about NVIDIA's new Blackwell GB202. This thing is the largest, most ambitious piece of silicon the company has ever designed for the consumer space, and we're going to tear it down and see exactly what makes it tick. So I can just throw a number at you, right? 92 billion transistors. But that doesn't really mean anything, does it? It's just a huge number. The real question is, what does that actually look like in the real world? How physically big is a chip with that kind of density? Well, here's some perspective. That tiny little square on the right, that's a Zen 5 CPU chiplet, something many of you are probably familiar with. And the absolute behemoth on the left, that's the GB202. The difference in scale is just staggering. This isn't just a big graphics card. It's a monster built on a scale we usually only see in dedicated, super expensive server hardware. So yeah, let's officially meet the monster. This is, without a doubt, the largest GeForce GPU NVIDIA has ever even attempted to build. Let's get right to the specs, the raw numbers. We are talking 92 billion transistors built on TSMC's 4N process. All of that is crammed into a single die that's over 760 square millimeters. And this one piece of silicone, it's the engine that's going to power everything from the flagship RTX 5090 all the way up to their professional AI cards. To really understand how this chip is put together, we're going to start our tour from the outside and work our way in. You can think of it as taking a tour of the shoreline. This is where all the I/O and memory connections live, and as you're about to see, they basically define everything else about the chip.
And it all kicks off with this one single number, 512-bit. This is the width of the memory interface, and it is, without a doubt, the single most critical design choice NVIDIA made. This one decision has massive ripple effects on literally everything, from the chip's physical size to its final cost.
So why is that 512-bit choice so unbelievably important? Well, to even get to 512-bit, NVIDIA had to physically line 3 of the chip's 4 edges with 16 little interfaces. We call them PHYs, that connect to the memory. That means the entire top, left, and right sides were spoken for. It only left the bottom edge for everything else. The main PCIe connection to your motherboard, the display outputs, everything. The whole perimeter was booked. And this brings us to the most crucial takeaway. The second NVIDIA's engineers committed to that 512-bit bus, the minimum physical size of this chip was basically locked in. They couldn't have made it smaller even as they wanted to, because they needed all that physical edge space, that shoreline, for the memory connections. It's not like they could just have empty space in the middle. Okay, so we've walked the perimeter, the shoreline. Now let's head inland, right into the heart of the compute engine. This is where the magic happens, with the cache, the cores, and all the processing clusters. Right smack in the middle of the die, you've got the L2 cache. The best way to think about it is like a giant 128 megabyte data buffer. Its job is to sit between the memory and all those thousands of cores, helping to manage traffic and, most importantly, keep those cores fed with data. If you're familiar with AMD's Infinity Cache, it's a very similar idea. Okay, now the official block diagrams can look a little intimidating, right? So let's just break it down nice and simple. The compute power is all organized in this hierarchy. At the very top, you have 12 huge graphics processing clusters, or GPCs. Inside each one of those, there are 8 texture processing clusters, or TPCs. Then inside each TPC, you get 2 streaming multiprocessors, SMs, and that's finally where you find the 128 CUDA cores that do all the heavy lifting. So when you add all of that up on a full, perfect die, the final numbers are they're mind-boggling. We're talking nearly 25,000 CUDA cores, hundreds of specialized ray tracing cores and AI tensor cores. It is an absolutely incredible amount of parallel processing power, all on one slab of silicon. But of course, all that power comes with a price tag. And I'm not just talking about the sticker price you see in the store. Let's shift gears from the architecture and talk about the economics and the sheer physical difficulty of actually manufacturing a single monolithic chip that's this big. This chart is awesome. It shows you exactly where all that silicon real estate is going. Now the compute part, the GPCs, taking up 44%. That makes sense, right? That's the engine. But check this out. The memory system and the L2 cache combined take up 30% of the entire chip. That's a massive investment just in feeding the beast. And here's the thing about making chips this big. It's hard. The estimated yield for a perfect chip is only 56%. That means that for every 100 chips that come off the assembly line, nearly half of them have some kind of defect that makes them unusable, at least in their full form. That's a huge manufacturing problem. So how does NVIDIA get around that? I mean, you can't just throw away almost half your product. Well, they do something called salvaging dies. The RTX 5090 that you'll be able to buy doesn't actually have a fully perfect chip inside. Instead, NVIDIA takes chips that have minor, tiny defects, they laser off and disable the faulty sections, in this case about 11% of the SMs, and then they sell that as a 5090. It's a really clever strategy to increase the number of usable chips they get from every single wafer. So, we've looked at all this architectural evidence, and it all leads us to the biggest question of all. When you look at these design choices, what was this chip really built for? Is it a gaming GPU first and foremost, or is it secretly an AI beast that just happens to be good at games? You know, the answer gets crystal clear when you just stop and think about what a pure gaming-first chip would have looked like. NVIDIA totally could have used a 384-bit bus. That would have provided more than enough memory bandwidth for any game imaginable. That hypothetical chip would have been smaller, cheaper to make, and less power-hungry. But they didn't build that chip. They chose the bigger, more complex, more expensive 512-bit design. And that points to a very different set of priorities. Because if you look at it through the lens of AI, all of these design choices suddenly make perfect sense. That 512-bit bus, yeah, it's total overkill for gaming, but it's absolutely essential for feeding gigantic AI models. It's what allows them to build workstation cores with 64 or even 96 gigabytes of VRAM. And tweaking the CUDA cores to handle integer math, that one change gives them a 4x jump in raw AI performance. This thing was built for AI. So with this whole bigger is always better strategy, NVIDIA has created an absolute monster, but it also means they're running straight into a wall, a very real, very hard physical limit. And it begs the question, can these single monolithic chips actually keep getting any bigger? And this is what that wall looks like. The absolute maximum size you can make a single chip with today's manufacturing technology, it's called the reticle limit, is 858 square millimeters. GB202 is already at 761. I mean, they are right up against the ceiling. There's almost no headroom left to grow. And that creates a massive problem for the next generation. To get another big performance jump, they can't just make the chip bigger. That option is pretty much off the table. They're going to have to either jump to a much more advanced and way more expensive manufacturing process like TSMC's 2-nanometer tech, or they're going to have to fundamentally change their entire architecture. Which leaves all of us with one final and kind of provocative question. Now that they've pushed this single-chip, monolithic design to its absolute breaking point, is a chiplet-based architecture, breaking one giant chip into multiple smaller connected ones, is that the only viable path forward for high-end silicon? That's really the big challenge facing the entire industry right now.